All right, ladies and gentlemen, this is going to be our next video on evolution, and this is following up on the video from allele frequency. So if you have not seen that video on allele frequency, I highly suggest that you watch that before this video, because this video will not make sense. What we're doing now is Hardy-Weinberg. We're introducing this concept to work on our Hardy-Weinberg problems. Let's get started on this next video. So in order to understand Hardy-Weinberg, we have to understand the word balance. Well, balance is a condition in which different elements are in the equal or incorrect proportions. So everything is in equilibrium. We're going to say the word equilibrium a lot when we go through and discuss Hardy-Weinberg. So if balance or equilibrium is maintained within a population's genes, can evolution occur? Let's go through and think about this. Well, if everything's in equilibrium, is the population going through and adapting, and are there environmental pressures on that population? Well, the answer is no. If everything is maintained and our allele frequency stays the same, it means that there are no environmental pressures and our population is not evolving. So let's go through and try to understand these pressures and how it has an effect on a population. Let's go through and look at this hypothetical mouse population here. We're going to have two sets of mice here. We're going to have mice with brown fur. We're going to have mice with black fur here. So if we look at this, we're going to say that there's a dominant allele for light-colored fur, and there is a recessive allele for dark-colored fur. We're going to look at this first generation, and we can go through and look at the genotypes. We can see that all of these brown mice here are homozygous dominant, and then all of these black mice here are homozygous recessive. So if we do our allele frequency calculations for this, well, we can go through and do it this way. Our p-value, or our frequency of dominant alleles, is going to be 0.5. And our q-value here for our recessive alleles is going to also be 0.5. Now what we're going to do is we're going to introduce a pressure. Let's introduce a fox, and the environment and now the camouflage and the ability for the mice to hide is going to have an effect on who survives, natural selection. So if we look at this, let's look at our second generation here. Well, our second generation, more of the brown mice survived and less of the black mice did. So now we can go through and do our allele frequency calculations here. And we can see, well, now we have 0.7 for the quantity, or 70% of our overall alleles in this population are for the light-colored fur, for dominant. And then for our Q, 30% or 0.3 are for the dark-colored fur. And then again, we're going to go to our third generation with the same environmental pressure here. And then we can see that as we get to generation 3, well, now we see mostly brown mice and a limited amount of these dark colored mice here because of their ability to camouflage in the grasses. So what we see here is 90%, or the percentage of alleles within the total population, is 0.9 for the light colored fur, or for the dominant allele. And then we see for Q, this is 0.1. And only 10% of the alleles within this population code for the recessive dark-colored fur. So we can go through, and if we look at these generations, what we can see is 0.5 plus 0.5 is equal to 1. P plus Q must always equal 1. We also have P plus Q for our second generation. 0.7 plus 0.3 is equal to 1. And 0.9 plus 0.1 is equal to 1. So we can see, remember, we're trying to go through and calculate allele frequencies here, P being the dominant allele, Q being the recessive allele. So what can we tell from this? Well, because our allele frequencies changed over time, natural selection was at play, and it meant that this population was adapting and evolving. So we're trying to make sure that we understand why we're going through and looking at this, and what this data set is telling me is this population is going through and evolving. Now let's look at the scenario as if there were no environmental pressures. So here's our first generation, and we're going to say that there are no longer any fox that are going through and putting any pressures on this population to go through and evolve. So now the mice can just go about their daily lives, and they can go through and reproduce and go to the second generation. And without the environmental pressures or the need to go through and adapt, what we see is we're going to see the same allele frequencies for our second generation and for the population. It remains at 0.5. And we're also going to see, in the absence of these fox and in the absence of these environmental pressures for the third generation, we're going to see the same allele frequencies here. So again, what we're trying to do is see whether evolution has occurred and see how it's going through and how it's affecting those allele frequencies over time. And then we can identify what factor or what is going through and causing the populations to go through and evolve. So the way that we're really going to look at this is with the Hardy-Weinberg equation. And Hardy-Weinberg equation came from Godfrey Hardy and Wilhelm Weinberg, both scientists, and they derived this equation here. Now it's p squared plus 2pq plus q squared, which is equal to 1, just like our p plus q is equal to 1. And it's going to show that the allele frequencies do not change in a population in the absence of evolutionary forces. So in the absence of these environmental pressures and these evolutionary forces, what we're going to see is the allele frequencies are going to remain the same. And how do we go through and derive this formula? Well, we have to look at individual alleles. So for allele number 1, we're going to get p plus q, which is going to be equal to 1. And then for allele number 2, we're also going to have p plus q, which is equal to 1. We're going to go through and FOIL this formula, and by going through and foiling and then simplifying the formula, that is how we get our p squared plus 2pq plus q squared, which is equal to 1. Now what's different about this formula is now we're going through and looking at the genotypes within the populations. We're not going through and looking at the individual alleles necessarily. So p squared is going to be the frequency of homozygous dominant genotype. 2pq is going to represent the frequency of the heterozygous genotype, and then q squared is going to represent the frequency of the homozygous recessive genotype. So remember, p is representing the dominant allele, q is representing the recessive allele. And what we're going through and doing is foiling the formula here, and then we're accounting for the individuals that we're going to see, the frequencies of those genotypes, both the homozygous, heterozygous, and homozygous recessive individuals within that population. Now, Hardy-Weinberg is only going to work in and only going to be in equilibrium when these 5 rules apply. So the thing that we have to understand is we are only in equilibrium when there are no new mutations occurring. So there are no new alleles being created in the gene pool. There is no migration, so no one is moving in and out of the population. There's also a very large population that we're going through and looking at, and that's going through and ensuring that we have a statistically significant amount of individuals to go through and distribute our alleles. The mating in the population has to be random, and that means that individuals do not choose mates based on genotypes. And then 5, there is no natural selection, so all members of a population have an equal chance of reproducing and passing their genes to the next generation. Now, when all of these conditions for the population are met, what this means is evolution/adaptation is not occurring. So there are no pressures, there are no evolutionary forces that is going to cause a change in our allele frequencies here. Now, the reason that we're going through and learning about all of this is there are going to be 2 fundamental and main reasons here. The first one is what we've gone through and talked about. We can determine which of the 5 pressures is going to cause the population to change. So we can identify what is going through and causing this population to change over time. The second reason that we're going through and learning about this is we're trying to also go through and see the prevalence of a specific gene or allele in a population. If I know what the prevalence of a gene or allele is and it's disease causing, I can go through and account for that, and then I can go through and try to eradicate that genetic disease from a population. This is particularly useful for doctors and scientists that are dealing with genetic diseases that have an influence on humans. So all of that is a ton of information. So I want to make sure that we review what each of these individual formulas mean and what each of the individual's terms mean from the last 2 videos. So P is representing the dominant allele. Q is representing the recessive allele. So we get one of the formulas that we're going to use, which is P plus Q, which is equal to 1 when going through and looking at allele frequencies within the total gene pool. Now, what we can also get from all of this is we can also look at the genotypes for the homozygous dominant, heterozygous individuals, and homozygous recessive individuals. For the homozygous dominant individuals, we're going to represent them by P squared. For the homozygous recessive, we're going to represent them with Q squared. For our heterozygous individuals, what they're going to be represented in the formula is 2pq. And the formula that we're going to go through and get from that is p squared plus 2pq plus q squared is equal to 1. Both of these formulas must always equal to 1. So in the next video, what we're going to do is work through these types of problems, how to go through and solve them, and how to go through and complete them on our exams. So, did you guys learn? Well, did you learn a couple of things? Did you guys go through and learn about the Hardy-Weinberg formula? Did you guys go through and learn about why we're using Hardy-Weinberg and why this is important when learning about evolution? And then did you guys learn about what each variable stands for in the formula? P squared plus 2pq plus q squared is equal to 1. P squared is the frequency of homozygous dominant genotypes or individuals. 2pq is the frequency of heterozygous genotype or individuals there. And then q squared is the frequency of homozygous recessive genotypes within that population. This is going to be the end of the video. I will see you all in class tomorrow.